Hi, I'm Robert Muth, and I'm a PhD student at TU Berlin and a Distributed Security Infrastructures group by our supervisor Florian George. I'll present SmartDHX, which is a Diffie-Hellman key exchange scheme fully implemented as an Ethereum smart contract. First, a brief recap or introduction to Diffie-Hellman key exchange. What you can see here are three participants, Alice, Eve, and Bob. Alice and Bob want to establish a secure encrypted communication channel because they assume that their communication is being monitored by some stranger Eve. For initialization, both agree on the parameters g, a natural number, and p, a prime number. They have to hold certain properties, but that's not important for now. Just keep in mind, both are public. Next, Alice and Bob generate a random number, a and b. For better understanding, all uppercase variables here can be public and all lowercase ones are kept secret by the participants. Next, both calculate g to the power of their random number, modulo p, and exchange their results. Finally, Alice and Bob calculate the exchanged number to the power of their secret random number, modulo p, and magically receive the same result that they can now use for establishing a secure channel. Eve at this point cannot deviate the same secret because Eve never experienced one of the secret exponents. But there's one problem left. When Eve can directly manipulate the communication between Alice and Bob, Eve could act as a man in the middle and exchange separate secrets between Alice and Eve and Bob. Due to the lack of authentication, this could go unnoticed. That's why utilizing blockchain for securing communication can be useful since blockchain users have a wallet, which you can see now at the top. It contains a private key, which we call lowercase p, and a public key. The private key then can be used for signing the transactions and therefore for signing capital A and B. So, when Alice and Bob exchange their public keys, the values cannot be manipulated unnoticed without compromising the integrity of the whole distributed ledger. Until this point, you can follow the assumptions of a related work from Patrick McCurry's key exchange protocol with Bitcoin. Now to SmartDHX. We have the same two users who want to exchange a secret key, but with a man in the middle on purpose, a smart contract. It can contain program logic, and the correct execution can be verified by everyone. That is why we put all the key exchange logic in there. Again, the same values will be exchanged as before, and still the transactions will be signed. The smart contract cannot change the values unnoticed because its code and execution can be tracked and verified. But the random numbers and the final secret key should not be exposed to the blockchain, of course. That's why the smart contract only provides the logic, but the execution of the marked lines here will only happen locally. Now let's have a look at the code, which is also available on GitHub. Here you can see a smart contract for exchanging a secret key between two of its instances. So Alice and Bob would deploy this smart contract separately. First, you can see G and P hard-coded since they are public. They were generated with OpenSSL. Then the capital B, the exchanged value of the other instance, and the address of the other instance. The solidity code at the end executes the key calculations as explained. Now the really interesting part. Here you can see JavaScript code which manages the smart contract calls and generates the random numbers. Let's have a closer look at it. First, it generates an array with 32 random bytes, which equals 256 bit. It will be passed to the smart contract instance by calling the solidity method generate_a. This method generates the uppercase public A value based on the secret random number. We added .call to the method so it does not submit a new transaction to the blockchain, which would reveal our secret random number. Next, we actually call the transmit method without .call, which then transmits the public capital A value to the other participant's smart contract. Finally, the JavaScript returns both A values. Now have a look at the truffle migration script, which shows how the JavaScript will be executed. It shows an exemplary key exchange between two of the smart contracts. So it would be executed by Alice and Bob separately. In line 6, the migration script loads the key exchange JavaScript code from the smart contract and executes it in line 7 in order to generate its public and private key values. Notice here that the migration script sends calls and transactions, so both, to the smart contract. But that is coded inside the JavaScript, which will be executed with a just-in-time code execution command eval. That means that generating the keys happens only locally, but exchanging the uppercase A sends a blockchain transaction. Next, when both instances exchange their values, the following code calculates the secret key. As you can see, all cryptographic logic, even sending transactions, is stored in the smart contract itself. Now, sometimes multiple parties want to exchange a secret key. They can therefore exchange keys between all participants. Either one single key per participant, like on the left-hand side, or multiple keys for a fully connected network. Or using the multi-party capabilities of Diffie-Hellman key exchange, which we implemented for minimizing the number of transactions. So one can either minimize the number of blocks or the needed gas, or like in our case, the number of transactions. For more details here, I'll refer to our paper. However, our evaluation reveals the pros and cons between the two-party and the multi-party key exchange between multiple participants. I don't want to go through the numbers now, but as a quick conclusion, multi-party can save transactions, but the gas costs increase tremendously, at least for our proof-of-work implementation. Last but not least, I'm not a cryptographer, but for increased security, one has to consider the source of randomness for secure key generation. That's why we utilize all of the JavaScript environment possibilities we have in Truffle Migration Script and implemented SmartDHX with using a secure random number generator included via npm repository, which has to be available then. And lastly, if 256-bit keys are not secure enough, SmartDHX can just be executed multiple times or extended to arrays of Solidity's maximum data types for exchanging multiple values per transaction. So, and why did we implement that? The proof of concept of a full key exchange protocol confirms our vision and leads to new use cases. Our vision is to bring more decentralized app logic into smart contracts so we can get rid of centralized server-side logic. We therefore improve the integrity between the user and the smart contract's communications. And we also make the code execution verifiable, which would normally be served by an external party. We are also evaluating additional security improvements, like with adding elliptic curve cryptography. And we evaluate other privacy-enhancing techniques for implementing in smart contracts. Lastly, one new use case with our technique could be opening sockets on the clients for off-chain side channels. And since smart contracts are sandboxed, we could fetch data with Node.js HTTP requests and use that within smart contracts. So, we're at the end now. Thanks for listening, and here you can find the source codes and our paper. If you have any questions, I'm happy to get in touch with you.